Section 5.3 Fundamental Theorem of Calculus. This section we will cover the area functions, which is the concept to understand fundamental theorem of calculus. And then we will see the relationship between the differentiation and integration as the inverse relationship of each other. For the area functions, by definition, let f be a continuous function for a less than or equal to t. The area of the function f with the left endpoint a is defined as the ax equals the definite integral from the lower limit a to the upper limit x of the function f of t with respect to t, where t is called the dummy variable or the variable of integration, where a is less than or equal to x. Note that the area function or the definite integral will give you the net area of the region bounded by the graph of the f and the t-axis on the interval ax. Examples: consider the trapezoid bounded by the line f of x equals 2t plus 3 and the t-axis from t equals 2 to t equals x. The area function ax is defined by the definite integral from 2 to x of the f of t with respect to t. And this definite integral gives the area of the trapezoid for x is greater than or equal to 2. Part A, we are going to find the area where x equals 2 and the area where x equals 5. That means the endpoint is 2 and the endpoint is 5, respectively. Part B, we're going to find and graph the area function ax for x as the general variable as long as x is greater than or equal to 2. And part C, we are going to compare the derivative of the area function a to the f, which is f of t equals 2t plus 3. For the first part, we are going to evaluate the area at 2 and area at 5. Let's sketch the graph of the function f of t, where it's defined by 2t plus 3. The slope is 2, and the y-intercept is 3, or 0, 3 as the y-intercept. And the left endpoint is 2. So when t equals 2, the function value will be 7. So let's make the increment somewhere over there, and then it's a straight line starting at 2 and on. So as we define x as the right endpoint and 2 is the left endpoint, so it's formed the trapezoid. And then the area under the graph is the area of the trapezoid from point 2 to point x. Note that the area of the trapezoid equals the 1/2 times the height 1 and height 2. Add them together, height 1 plus height 2 divided by 2 and multiply by the base. And the base is the difference of the x and 2. Okay, for a at 2, that means the x equals 2 or the right end is 2. Then the area of the trapezoid, follow the formula to find the area, is 1/2 times the height at the left end point plus the height at the right end point, and then multiply by the difference or the base, which is the difference of the left and the right end, which is 0. Therefore, the area where the right end is 2 is going to be 0. If you see the graph, so that means you start at 2, you stop at 2 also. So that means no area formed or no trapezoid is formed. Therefore, the area is 0. And then for a equals a at 5, or the right end is at 5. This time, we're going to find the area using the trapezoid area formula, or 1/2 multiplied by the sum of the function at the left end and the function at the right end, multiplied by the difference of the right and the left end, which is 5 minus 2. Then we get 1/2 multiplied by, recall the function is defined by the 2t plus 3. So this f at 2 is computed as 2 times 2 plus 3, and the f at 5 is 2 times 5 plus 3. And the number comes out to be 7 for the f at 2 and come out to be 13 for the f at 5 and the 5 minus 2 equals 3. Then the number is simplified to be 20 divided by 2 or 10 times 3 or 30. So then the area of the trapezoid where the left end is 2, the right end is 5 equals 30. The next part, we are going to find and sketch a graph of the area function a of x for x greater than or equal to 2. Let's sketch the graph real quick for the graph to represent the area under the graph as the area of the trapezoid from 2 to x. So as we find the area ax, that means for any right end point as a x, which is computed to be 1/2 the function at the left end plus the function at the right end multiplied by the difference of the right and the left end or x minus 2. Again, the function goes with the 2t plus 3. F at 2 is 2 times 2 plus 3, which is 7, what we computed earlier. At x, gonna be 2 times x and 2 times x plus 3. Now we get the simplified form as 7 plus 2x plus 3 multiplied by x minus 2. 7 and 3 simplified to be 10. Then we have 1/2 multiplied by 10 plus 2x multiplied by x minus 2. 10 plus 2x is 2 times 5 plus x. 2 and 2 reduce. And now we get the product of 5 minus 5 plus x and x minus 2. Distribute or multiply these two factors or these two polynomials to get 5 times x, 5 times negative 2, x times x to be x squared and minus 2x. That comes out to be x squared plus 3x minus 10 as the area for the trapezoid that has the left end at 2 and the right end at x. And this is the parabola. Okay, for the y-intercept or where x is 0, the y-intercept is negative 10. But at 2, so the area at 2, if we follow this formula, we get 2 squared plus 3 times 2 minus 10 or 4 plus 6 minus 10 and turns out to be 0. That tells us the x-intercept is at 0. After the value, the t equals to, the area will become positive and it goes with the parabola graph as the area. So actually this is the area function. The area is the parabola. Sorry, let's clean up a little bit. So get the graph of the area as increasing. It's increasing as t increasing. Now, in part C, we're going to compare the derivative of the a to the f. Recall the ax that we got from part B as x squared plus 3x minus 10, where the f of t is in the form of 2t plus 3. Now for the derivative of the a, which is, since a is the function in x, so we find the derivative with respect to x of the function ax, or the derivative of x squared plus 3x minus 10 gives us 2x plus 3. When we compare the derivative and the function f, this is the same as the function at x. Now we can see the relationship for this situation as d by dx. The function ax is defined as a definite integral from point 2 to the point x of the function ft with respect to t. And it turns out to be 2x plus 3, which is the f of x. And this will lead us to the fundamental theorem of calculus part 1.